The second and more common type of indicator electrode that's used is an ion selective electrode. And I have here an image from the online textbook that shows sort of a general schematic for ion selective electrodes and how they work. The heart of an ion selective electrode is down here at the bottom, this ion selective membrane. And this membrane can be made out of many different materials. And so this discussion we're going to have here is going to be general. And then we'll start looking at some of the specific ways you can construct these ion selective electrodes. So the first type of ion selective membrane that was discovered is actually glass. This is what's used for a pH electrode. There are also other types of solid crystals that are used as this ion selective membrane. So for example, the chloride ion selective electrode we've used in lab uses this. Other halide, including fluoride and others, use the same type of membrane. And there are also liquid-based membranes. I'll put liquid in quotes because, of course, it's not an actual liquid because then it would flow off of your electrode. But these liquid-based membranes are another type of ion selective electrode that's used. And so we'll talk about each of these. But let's talk about, first of all, the general picture of what's going on here that'll apply to any of these types of membranes that are specifically used. So the ion selective electrode is made out of two reference electrodes. So we have one on the inside of the electrode and one on the outside that goes into our sample solution. And the purpose of these is that we'll have our measured potential, so we measure on a potentiometer, is going to be the difference between our reference electrode on the sample side minus our reference electrode on the inside of our potentiometer. Then we'll, of course, measure a junction potential. And importantly, we'll measure what the potential is across this membrane. And so everything else, so these first three values will be fixed, ideally, right? So these shouldn't change. Now, that's the whole point of a reference electrode, is that its potential doesn't change. So either our inside or outside reference electrodes, those should stay the same. And the junction potential should stay the same even as concentration of our sample changes. But on the other hand, the potential of the membrane, this depends directly on the activity of the sample. And so we can write out an equation to represent this. E membrane will be equal to some, now we don't have a standard potential for the membrane, but we'll call this E asymmetric, minus, and we can write out like the next equation, 0.5916 volts divided by N. Now this, of course, is assuming that we have 25 degrees Celsius temperature, right? All the usual substitutions that go in to get this number here, times the log of the ratio of our activity on the inside and our activity on the outside. And this ratio is what matters. Now, what we can do in this is that this internal solution, right, this right here, let me pick a different color you can actually see. Let's do red. This right here, this internal solution, we control this concentration. And it's fixed. So this is going to be a constant. This E asymmetric, this ideally is zero. Basically, when the internal and external activities are equal, there should be no potential across the membrane. In practice, that's not the case. There's usually some asymmetry here. But that's a fixed value. That's just a number. And so what we can see is that overall, we're going to have E measured, I'm going to lump a lot of things together, will be equal to some constant we'll call K here. minus 0.05916 divided by n volts. And K takes a lot of stuff into account, we'll talk about in just a second, times the log of the activity of the outer solution, or what's called a sample in the figure. Because everything else is fixed, we can lump, right, this term here, the reference electrode, the other reference electrode, the junction potential, this E asymmetric, as well as, you know, we can sort of factor out this internal activity, lump all of that together into this constant K. We can't necessarily know what that's going to be in advance, but it's something we can calibrate. It should be constant. And so it just ends up being the y-intercept on our calibration curve. And we end up with the potential depending only on the activity in our solution. And so this gives us a linear relationship between the measured potential and the concentration of our species in solution, or more accurately, the activity of our species in solution. And so this is the general idea behind how we can measure the concentration of a species in solution using an ion selective electrode. So we need these two other reference electrodes to measure the potential across this membrane. But if we fix the concentration or activity of our analyte on the internal solution, then things only depend on this external, on the sample solution, on that concentration, or actually on that activity. And so this gives us a way to measure concentrations. So once we do a calibration, we can find out the activity of our solution and use this to measure unknown samples. So this is the basic idea, and we will look at how these membranes function and how they produce this potential in the next few videos.